In this video, we're gonna discuss step 1 of the proof of transversality homotopy theorem. But the setup of this theorem is that we have a map F here from a manifold M right into a manifold N. Okay, and this is F of M. And then we have an embedded submanifold Z of N. Then the theorem claimed that we can always deform this F so that it becomes transversal to Z. We then said that the first step in the proof is to extend this map to a family of map from M into N, such that the family, when viewed as a map, is going to be transversal to Z. In that case, most members of the family are going to be transversal to Z, but these members are all going to be homotopic to each other, and in particular to this little f. So that means that we have found some map homotopic to F and transversal to Z. Okay, so now let's discuss the first step. Let's try to construct such a family. Okay, so to motivate the ideas in the proof of step 1, let us dream a little happy dream and assume that N is actually some Euclidean space. For example, in this picture, I'm drawing N as R2. Then there is actually a very easy way to extend this F to a family of smooth maps. The idea is to take the parameter family to be the unit ball inside this Euclidean space Rk. For example, in our case here, I'm drawing this as the unit disk in R2. Then we can naturally extend F, this little f, to a family, big F, on this whole product as follows. So for every point P, it should map this slice at P to this ball center at Fp. In formula, this map sends every point S, P here, so I can draw it like this here, to the point Fp plus with S. So let's say S corresponds to this vector here, then we just map this point S, P to this point, which is obtained by translating Fp by S. Basically, the idea is we have a unit disk center at P here, and we just take that exact unit disk, right, and put it here, but put the center at Fp. This would give us a family of smooth map from M to the Euclidean space. At every point S, we have a map Fs, which is just Fs, blank, right, from this copy of M into the Euclidean space. And this family is super nice because it's transversal to every submanifold of this N. Why is that? Well, that's because it's a submersion at every point. The tangent space at every point of the unit ball is a full Euclidean space. Thus, if we take any submanifold Z of N, right, then at any point in this intersection here, we see that the tangent space to the image of the family already generates the full tangent space to N. Not even need the tangent space to Z. Thus, in conclusion, because this map F is a submersion, it's going to be transversal to every submanifold Z of N. Okay, so we see that when N is a Euclidean space, then we can easily prove step 1, i.e. we can easily extend this map F to a family, a smooth family, that is transversal to any submanifold that we like. Why did we need N to be Euclidean space? Where did we use the fact that this is a Euclidean space? Well, we use the fact that N is a Euclidean space here when we give this formula for the family. Here we use the vector space structure of the Euclidean space, right? On a general manifold, we can't just add points. It doesn't make sense. Does that mean then this construction will not work for a general manifold? Well, the good news is that it turns out by Whitney embedding theorem that every smooth manifold can be smoothly embedded inside some Euclidean space. Actually, we can even say more. If the dimension of this manifold is, say, liter n, then we can actually choose this k to be 2n plus 1. And actually, we can even require this smooth embedding to be proper. But we do not need all of those things right now. For now, we'll just assume that n is some embedded submanifold of some Euclidean space. Then in that case, we can still construct the family big F this way using this formula. This formula still makes sense. Okay, but now that n is not the full Euclidean space, then we have another problem. How do we know that the image of this family is gonna lie inside n? What if, for example, n looks like this? Then maybe we can change this formula a little bit. Maybe we can add a retraction map in here. That is, maybe we can find a smooth map right, on this image of f that sends every point in this image to n, to some point in n, in such a way that it is the identity on n. And thus, it retracts this whole image of f into this n. But this picture is misleading because this n might not lie inside this image of f though. The good news is that there will always exist a so-called tubular neighborhood of this n inside Rk which retracts to n. So, what we can do is that we can modify our family f a little bit so that its image is gonna lie inside this tubular neighborhood. And the way we'll do that is by changing the radius of each of these disks center at each of these fp. Fp plus s might be a bit too big. It might take us outside of the tubular neighborhood. So we'll find a way to scale each of these points down, right, so that we actually get a point inside the tubular neighborhood. So we'll introduce some multiplication factor here. Once we can guarantee that this point here lie in the tubular neighborhood, then we can just use the retraction map from the tubular neighborhood to retract it to a point in n. So that's the idea behind the construction of this family, but we haven't explained what a tubular neighborhood is. That's what we will do in the next video.